Hello, sir. Dr. Basu.
Hello. Hi.
Hi. It's what I should say. It's good morning or good evening.
It's almost 10:30 in the night here. So
10:30 p.m.
yes. 10:30.
Oh my God. So there is the 2-hour session. So 1.5 hour for talk, and after that, if for question answering. So almost 1.5 hour will be sufficient.
I think we have to probably reduce it to 1 hour or a little more because I have to leave. It's pretty late and I have a class tomorrow morning.
Okay,
So,
not an issue. Not an issue.
I will let's try to wrap up everything within an hour, including my presentation.
Okay. Not an issue. Not an issue. We will start at 10 a.m. sharp here.
Okay, sure.
After 5 minutes, let all participants join. Then we will start.
Sure. Okay. Dr. Ray, do you want to start now? I think it's 10 a.m. in India, right?
So, good morning, participants, to all. Let's welcome for the uh, first session of second day. And before start of the talk, let me welcome Dr. Kanad Basu from Assistant Professor from the University of Texas at Dallas, Texas, USA. Dr. Basu received his PhD from the Department of Computer Science and Computer and Information Science and Engineering, University. His thesis was focused on improving signal observability for post-silicon validation. Post-PhD, Dr. Basu worked in semiconductor companies IBM and Synopsys. At IBM, he worked on the design of IBM Power and Z processors. At Synopsys, Dr. Basu helped develop DFT Max Ultra, the state-of-the-art low-pin hardware test solution. Before joining UTD, Dr. Basu was an assistant research professor at the Electrical and Computer Engineering Department of NYU. He has authored 2 US patents, 2 book chapters, and several peer-reviewed journal and conference articles. Dr. Basu was awarded the Best Paper Award at the International Conference on VLSI Design 2011. Dr. Basu's current research interests are hardware and system security and AI hardware. At present, he has published more than 100 research articles in reputed international journals and conferences, which is well recognized by eminent academicians and researchers throughout the globe, and achieves 1,085 citations till today, having H index 16 and I-10 indexed 19. So I welcome Dr. Basu to deliver his talk on antivirus hardware in new domain of system security. Over to you, sir.
Thank you. Thanks a lot, Dr. Ray. Thanks for inviting me. And it's great pleasure to be able to talk with all of you here, all the attendants. I'm not sure whether all of you are from NIT Sikkim or from outside the campus also, but I think there are a lot of people I see from outside, so it's great. Unfortunately, it's pretty late here, so I won't be able to stay awake too long, but I'll try to share my presentation during this time. I have a small relationship with NIT Sikkim, so this actually made me very happy when Dr. Ray invited me. One of my old childhood friends, he is a faculty in the EC department of NIT Sikkim. So that's a small connection I have with NIT Sikkim. But without further ado, let me actually share my screen so that we can. Okay. I hope all of you can see my screen, right?
No, sir. Let me stop presenting. Yes, sir. Yes.
Can you see full screen? Okay.
Yes.
Since I'm presenting in full screen, I won't be able to see if you type in any chat messages. So either please speak out, or if you type, I will request Dr. Ray to read it out for me. Okay?
Sir, they will talk at the end of your talk. We will follow all the chat queries as well as their direct queries through microphone at the end of your talk.
Okay, sure, sounds great. So welcome everyone. So today my talk is about antivirus hardware. This sounds a little new, right? Because most of you probably have seen antivirus software. By seen, I mean it cannot be seen. It's a software. So by seen, I mean you have heard about it or installed it in your systems, right? But this is a new domain of research that we are doing, and not only this has been used in the industry very recently. So we'll talk about that. So this is an outline of my talk. First, we'll talk about 2 challenges, system and hardware security. First, let's talk about system security. So we know that antivirus software is typically used to detect any form of malware or any virus, as we say. So as I'll discuss shortly, virus is actually a subclass of the superclass called malware. So malware can be of various types. They can be viruses, there can be worms, there can be ransomware, and so on, right? So antivirus software is the common generic name used for any software that is used to detect or take out malware, right? So probably you have used antivirus in your systems. Now, recent research says, and Symantec, as you can see from the screenshot here, is one of the biggest antivirus development companies. One of the security experts there said that the antivirus software is dead. Why did he say that? So there are two reasons. One, modern malware are becoming very, very sophisticated. It's very difficult to detect them using traditional antivirus software. And we'll describe in this talk as to why that is the case, why antivirus, modern malware are more difficult to detect using antivirus software. The other problem is, if you remember, I don't know how long you guys have been using computers, but when I was using a Windows Vista machine, maybe a decade ago or like Windows Vista machines used to be really slow when you would use an antivirus software, right? And even today, if you use an antivirus software, you know that your machine is going to be slow. Now, you're working on a PC, on a computer, most likely. Now, imagine if you're working on an IoT edge device, for example, a smart pacemaker or a smart drone that is being used for a warfare, right, in the army. So those devices are very small. They have a very low battery life. They're very energy capable. An antivirus software on top of them, you're burning down a lot of energy. So imagine a system which itself has a low energy and you are using something that will burn out more energy. Your efficiency will reduce. You will no longer be able to use the system for a long time. People are trying to think beyond antivirus software for modern IoT edge devices, right? Okay, moving on. The other thing that we'll talk about today is hardware security. So security is no longer restricted only to software or network end. It actually has infested a hardware design cycle. So if you see this picture shows a very simplistic high-level view of how a hardware is designed, right? So initially you design the hardware using some sort of hardware languages like VHDL or Verilog. Those of you who are from EC background or maybe from the computer architecture background might recognize these names. So once we develop the hardware using Verilog or VHDL, there's a step called logic synthesis, which transfers that to a gate level netlist, like full of AND gates, OR gates, flip-flops, and so on, right? Then you do a placement and route, where you route it on a 2D plane, where you have all the transistors and the wires connecting them. Then you send it to a third-party a fabrication facility to fabricate the chip, right? And then you get the fabricated chip. You do some bunch of tests, like test or post-silicon validation. We're going to talk about this towards the middle of the presentation today. You do these tests, and then you get the final IC. You do some PCB assembly, and then you send it to a customer, right? That's a full flow. Now, the challenge is, in old days, like in pre-globalization, companies like IBM used to make everything themselves. For example, in New York, in their own head office, they would do everything themselves. But things have changed. Right now, it's no longer feasible for all companies to do it themselves. For example, a lot of companies don't have the fabrication unit, if you see in this picture. So that's why when I was talking, I said out third party, because a lot of companies that you know, that you use every day, for example, Apple. I'm sure some of you might be using an iPhone or a MacBook or so on, right? Apple doesn't have their own fabrication facility. They hire a third-party fabrication unit to manufacture their chips, right? Then some companies like Qualcomm and even the software companies, like, for example, I use a Google Nexus phone. Google doesn't have a fabrication facilities. And moreover, as Dr. Ray was saying, I worked in Synopsys and IBM. So Synopsys is a third-party EDA company that develops the EDA tools that are used for each of these steps. So Intel, for example, procures these third-party EDA tools to run their steps. So you see a lot of third-party players coming in. It's no longer a single company. A lot of companies are working towards a single chip development. So for example, even if your chip is developed by Apple or maybe say Samsung, that chip has a lot of different components formed by different companies. Now, what happens when these third-party entries, they create some problem, they create some security vulnerabilities. Now, imagine the situation when this is due to some army or navy or any military applications, right? So, for example, if the Indian Air Force procures some chips and they are made by some third-party manufacturing companies, there might be several security risks. One is counterfeiting. So, if you look at two pictures here, one is a real IC and the another is a counterfeit IC. It's difficult to identify which is a counterfeit IC, right? Both look very same. Just for your information, the one on the right is a counterfeit IC, which looks more clear, right? That's a counterfeit IC. Then you have overproduction. We'll talk about these. And then you have reverse engineering, where somebody can reverse engineer your design. And then you have something called hardware trojans, which we'll also talk about towards the end of the presentation. Okay. But these are the challenges of hardware security that has crept into modern hardware system design. So now we'll talk about each of these issues. First, let's talk about system security. So malware attack. As I was mentioning, malware or malicious software there can be multiple of them, and they are creating havoc in the society. So they can steal money, they can cause various attacks, they can steal private information, and there can be various types of malware. Ransomware. Ransomware means they will, like, you know what ransom means, right? Whenever somebody blackmails you, they can ask you for ransom. So they might say that, oh, we locked your computer, you pay us some money, and we will. So then let's look at some of the examples. For example, University of Utah and University here in the United States, they had to pay almost $500,000 in ransomware attack on this computer. So what happened is that these malware guys, they hacked the computer and they asked, like, pay us $500,000, otherwise we are not going to release. They're going to release the private information, confidential information of the students. This thing happened last year. I'm not sure how many of you were following this. So there was a huge gas pipeline. By gas, I mean petrol. In US, petrol is called gas. There was a huge gas pipeline from all the way from New Jersey to Texas, and that was hacked. So due to hacking, there was a huge supply flow problem, and as a result, the petrol prices in US rose up very high due to this. Okay. A large Florida school district was hit by ransomware attack. The hackers demanded almost $40 million for that. Stuxnet, this is a very interesting thing. So, a modern power grids, the grids that give power to your homes, your offices, your universities, or everywhere, they get a lot of computer. They do a lot of computing. It's not the dumb power grids of the 70s or the 80s where they're just mechanical components, right? They're smart components. They're connected to the internet. So Stuxnet was one of the first malware that was deployed on a power grid system that actually caused havoc. So imagine if you guys are in Sikkim and say there's a power grid and somebody creates an attack in there and the whole NIT Sikkim loses power. None of your classes will be taken. This type of conferences cannot happen. This will be a really bad situation, right? Then we have cars. So modern cars have more electronic components than mechanical components, right? As a result, cars can be hacked. And by cars, I don't mean the self-driving cars of the future. I mean the cars that we drive every day. These can be hacked. And we'll see some of the examples that have happened in future. So also Acer, I know some of you might be using Acer computers. Acer reportedly targeted a $50 million ransomware attack. So 22 Texas towns here in Texas were attacked with ransomware. So by towns, I mean the municipality of the towns where the whole function of the military was stopped. Now malware, you can see, is exponentially growing over the time. So in 2003 and 4, the number of malware samples were very less. In 2007 or 8, it's more. See, one thing I want to mention here, this is more of a philosophical thing. In 2003 or 4, we had very little internet connection, right? So mostly we used to use internet for checking our emails, or maybe, say, applying for some position, buying some railway tickets or something like that, but nothing more. Nowadays, all of us do net banking. All of us are doing social media. All of us use it for, like, for example, we are using internet for having an online conference, right? You couldn't imagine this thing in 2004, somebody from Texas presenting to in Sikkim in the middle of the night without traveling. That was unimaginable in 2004. Although internet has its boons, it carries with it these banes, if I can say the word. So if you can see here, the number of malware is increasing very much. And this is not restricted only to PCs. The number of malware in Android domain is also increasing. So we have 4 million new malware samples per year in 2017. So what are the different types of malware that are difficult to detect using traditional antivirus solutions? There are two modern types of malware which are difficult to detect. These are polymorphic and metamorphic malware. So polymorphic malware modifies itself in each iteration, and metamorphic malware rewrites itself in each iteration. So each version of the source code in metamorphic malware is different from the previous version. So as you can understand from the name, it has the phrase morphic, right? Morphic means modification. Probably we all studied metamorphism when we were studying what was it called, evolution in our biology in your high school, right? So morphic means change. So if the malware changes its structure, it's difficult to detect that. Why is that the case? Let's see. So let's find out how traditional malware are detected, right? So traditional malware detections are of two types: signature and behavior based. So let's first look at signature based malware detection. They store a bunch of software signature. So whenever a new program is run, software is extracted from its executable and matched with a set of known signatures. So for example, we are working on Google Hangout, right? Like I'm running it on Google Chrome. You might be running it on, say, Firefox or any of the web browsers. Or if you can work on, I'm presenting Microsoft PowerPoint, that's also a software. So whenever a software is running, what this does is signature-based malware detector, it will extract the signature from the executable of the software and match it against a set of known signatures. The problem is this can be easily subverted because it's a software. So an antivirus software, its privilege level can be subverted using a higher condition malware. And it's ineffective for morphic malware. So what happens is, if you change the software structure, as we did in the metamorphic malware, if you change the software structure, the executable changes, and as a result, the signature will change, right? And hence it cannot identify. So if you look at the picture here, we have Spider-Man and Peter Parker. They're one and the same guy, right? However, we cannot identify the difference between the two if the face changes, because signature-based malware detector can identify only by face. So what can we do effectively? So the second technique is behavior-based malware detector, which extracts the software behavior. It extracts how it will behave and not how it looks like. Like, for example, if you think of a GPS malware, the GPS malware will infect the device, will hide itself, log in the device confidential information, and will transmit it outside. It will perform all these steps, irrespective of how you write the malware, how you compile the malware, whatever the executable is. The final malware behavior will be the same. So behavior-based malware detectors can actually detect between Spider-Man and Peter Parker. And you would ask, why are we not using it? What's the problem? The problem is it is a very high overhead. Hence, it's not practical for PCs or IoT devices. It's good for research in the back end, but not exactly well if you are operating on a personal computer, okay? So that's a problem of traditional antivirus software. So how do we handle this? So researchers came up with an idea of hardware-based malware detector. So the whole idea is hardware features are much more trusted compared to software. They're much more difficult to undermine. So imagine if you have to subvert a hardware, you have to actually go and physically tamper the hardware, right? You cannot do it remotely. A software can be tampered remotely, right? Through internet and remote access. A hardware, on the other hand, you cannot do it without remote access. So therefore, people started using trusted hardware features for malware detection. And for the first hardware feature they used is a hardware performance counter for HPCs. What are HPCs? HPCs are dedicated registers found in all computers. They're found in the computer that you are using currently. They record certain architectural or macro-architectural information like number of branch misses, number of cache misses, etc. So they are already there. So reutilizing them for malware detection doesn't incur any hardware overhead. This is zero hardware overhead, right? So why do they perform well for malware detection? This is an example that I've shown. So we have plotted two HPC values, which are L1 exclusive hits, L1 cached exclusive hits, and the number of arithmetic microoperations executed. And these are several spec benchmarks. For those of you with a computer architecture background will know that the spec benchmarks are used to characterize any architecture once this is developed, okay? And you can clearly see each benchmark has a distinct characteristic of the variation of the HPCs, right? For example, if you see the benchmark HMMER and look at the L1 exclusive hit, it's different from any of the other L1 exclusive hits for any of the other programs. So you can clearly identify a program by creating a signature from these HPCs. And these signatures are difficult to jeopardize because these signatures are created from the hardware, not from the software. And then you can train a classifier to distinguish whether it's a malware or a benign program. Okay. So the industrial application, Intel has actually adopted this strategy. Intel is working with Microsoft Defender endpoint protection to protect against crypto miners, to detect crypto miners using CPU telemetry, which is a form of HPC. So what did we do? What was our contribution? So the first thing that we did is we developed a theoretical model for HPC-based malware detection. So till now, the HPC-based malware detection was completely empirical. So we were the first team that developed a theoretical model for HPC-based malware detection. And we found out the probability of detection increases with the increase in the number of HPC events and the reduction in the and the reduction in the sampling interval. So one thing that we need to know here is that modern hardware has multiple HPCs. Like an Intel processor, there's almost hundreds or 200s of HPCs. So, however, only a few of those HPCs can be monitored simultaneously. So, for example, in an Intel processor, you can simultaneously monitor only 4 to 6 of these HPCs among the 100, right? That's a bottleneck you have for HPCs. So, how do you do HPCs in malware detection? You use machine learning classifiers trained in HPC data. They're deployed on hardware-based malware detectors. These HMDs efficiently detect malware activity. And the question is which machine learning classifiers are best. So to collect the HPCs, what we do, in Linux, you have a tool called perf command that is used to detect HPCs. So, for example, the branch instructions, as you can see here, is one of the HPCs that we use, right? It gives the number of branch instructions every cycle. And a.out is the executable, and it monitors the one is every 1 millisecond it will monitor the HPCs and will give us the values. So this was our experimental setup. Of course, we cannot use our own computers to run the malware, right? Because that will infect our own computers. So we used a Raspberry Pi. I hope all of you know what Raspberry Pi is. We used a Raspberry Pi to conduct our experiments, and we collected HPC values for 300 benign and malware programs. The benign programs included various sorting and computational algorithms. We obtained a process-specific malware from VirusShare. This is very interesting for those of you who are not involved in malware research. VirusShare is actually a pretty cool website that holds a bunch of malware. So you can create a login and download the kind of malware you want. They will tell you whether this is malware for x86 processor, Intel ARM processor, AMD processor, and so on. Okay. So the impact on output is analyzed by using various machine learning classifiers. We use 7 different machine learning classifiers, as we'll show in the next slide. This is a picture of a Raspberry Pi. For those of you who are not aware of this, it's like pretty much a basic mini computer, and it costs like around $50. So the classifier comparison, we compared various machine learning classifiers like decision trees, nice BAS, k-nearest neighbors, linear regression, random forest, support vector machines, and neural networks. So we saw that the random forest performs the best, and we saw that utilizing inferior parameters can produce classifiers that perform suboptimally. This paper was presented in ISVLSI last year. Now we look at adversarial attacks on HMDs. So adversaries have produced attacks that can obfuscate HPC traces. So what does this mean? So basically, that means that you can run, for example, you're running a malware, you can run a benign program in the same thread, and that will perturb the HPC values, right? The HPC values will change the benign program HPC values. So how do you prevent against that? You can reverse engineer the HMD, use an adversarial sample predictor, and use an adversarial sample generator to generate the adversarial sample that can actually create a different output, and therefore that can create an adversarial example in misclassifying the malware. Okay, so how do we prevent against this? We create moving target defense. The whole idea is, see, the first step on generating the adversarial sample was reverse engineering the machine learning classifier, right? We stop that. How do we stop that? Remember, I said a modern processor has hundreds of HPCs, but among them, only 4 of them can be monitored simultaneously. So we change which 4 you can monitor simultaneously. So we built a bunch of classifiers, each with a different set of HPCs, and we randomly select a classifier for inference during runtime, right? And as a result, it cannot reverse engineer the classifier that was still attacked, and we can restore our performance. So while it dropped to 51%, with our defense, it improved to 72 and 77%. This paper is in TCAT this year, and you can easily download this paper from internet. So then malware detection in automobile ECUs. So let's look at two of the examples here. So in 2015, Chrysler, a big American car manufacturing company, had a case. The Jeep Cherokee that it was built, somebody hacked it. And there were two hackers who are like researchers like us. One of them was sitting in an office like we all are sitting right now. The other was driving on a highway. The guy who was driving on the highway suddenly saw that he had no control over the brakes and the accelerator. So what happened? The guy in the office could actually control. Imagine you're driving like that. Say you're driving from Sikkim to Calcutta, and on the highway, and you don't have control over your brake and your accelerator. It's a disaster scenario, right? The screenshot on the right shows a ransomware that was developed by McAfee. So McAfee showed to the world that this can exist. So basically, they have blocked the system and brakes, as you can read from the screenshot, right? This is a ransomware for a car. So the car was blocked, and unless you pay money, it won't be released. So let's look at malware detection automobile ECU. So a vehicle is a plethora of attack surface. It is the ECU, or the electronic control unit, the infotainment system, the telematics unit, the keyless entry system, the transmission control unit, and so on. See, unless you are driving an Ambassador in India, in that case you are safe, you're pretty unsafe otherwise. So compromising each of these can actually engender, because you can have malware infected. And the ECU, or the electronic control unit, is the most dangerous part. The attackers can triple the brake or eavesdrop on the victim. So we developed a crankshaft modification attack. So what happens is we send an erroneous value to the crankshaft, right? So long story short, what happens due to that is the brakes are applied very slowly. So for example, if you're driving and something comes to the front and you want to apply a sudden brake, that won't work, right? That's what the attack was. We actually did it in one of the cars. And we used HPCs to detect them, and we saw that we can do different classifiers, and autoencoders perform the best. And we used, this paper was published in Date in Europe this year. The other thing that we did is children's privacy detection, violation detection. So in the US, the number of children owning their own tablets and smartphones are increasing exponentially. As a result, the crimes against children have also increased. So recently, there was a data breach by Kids, a company that released information for 1,700 children. And this is very dangerous. So the Federal Trade Commission in Washington, D.C., they created a rule called COPA, or Children's Online Privacy Protection Act, which aims to ban apps or fine apps which are developed for children and they violate COPA, valid privacy regulations. So imagine if you have a kid somewhere aged 2 to 13, and he or she is playing a game, and somebody knows that there's a kid at this point who's playing the game, it can lead to child trafficking. This is very dangerous. So what should we do? So FPC periodically fines companies, like they fined Mobi and TikTok several money, and Facebook was fined $5 billion penalty. But however, there's no app on the end of a guardian, right? For example, if you're a parent, you don't have an app to control whether the app that your child is playing that's COPA compliant or not. We developed a tool for that using HPCs, and that appeared in NIT Tips last year. This got significant media coverage. We were featured in CBS and NBC, two of the biggest media outlets in US. They interviewed me for this. Now, these are the good things that we saw using HPCs, antivirus systems. But what are the disadvantages? Let's look at the disadvantages. HPCs are non-deterministic. The same program running on the same system can have 5% difference in HPC readings. They incur very high false positive rates. So benign software may be classified as a malware. The HPC readings inside a virtual machine differ from those on actual hardware. So if you know of any malware research, they typically do it on virtual machines, but you cannot do that in HPC. That's why we actually ran it on Raspberry Pi, because that's a bare metal code. It's not real time. You need to stop the system to collect the HPC data. So what are the alternatives to this? So we developed a proposed idea, which is trace buffer-based malware detection. So To understand that, let's take a step back and first understand what a trace buffer is, right? So this is a very simplistic, more simplistic picture of how a hardware is designed. So before a hardware is manufactured, you have implementation at the gate or RTL level, and you need to verify the design. You do pre-silicon verification. There's an oft saying that for each design engineer, you have 4 verification engineers, okay? So after chip is manufactured, you will undergo 2 tests. One is manufacturing testing and there is post-silicon validation. Manufacturing testing is used to detect any electrical faults, like opens or shorts in the design before you send the chip to a customer. Post-silicon validation, on the other hand, is used to detect any manufacturing, any functional faults, right? That have escaped the pre-silicon verification test and have manifested itself in the manufacturing chain. The design validation complexity has been growing exponentially over the years. Post-silicon validation as a percentage of total design resources have been growing also. The main problem with post-silicon validation is the limited observability. So let me give an analogy. So when you are running a C code or a Java code, when it doesn't work, or if you get a fabric, or if you get a segmentation fault, what do? You typically, sorry, it's pretty late. So you typically create something called breakpoints, right? And you observe internal variable values. You cannot do that in case of a hardware because the hardware is already manufactured. So you cannot break open the hardware and observe the internal values. So post-silicon validation, you can only observe the inputs and outputs. To solve this problem, researchers came up with something called the trace buffer or the trace memory. A trace memory is a part of a buffer or a hardware that stores some of the internal signal states. So it acts like your breakpoint. However, which signals you will observe are determined pre-designed because once the chip is manufactured, you cannot route the wires to the trace buffer, right? The question is less than 2% of the signals are selected. Which signals to choose? Now, this is a very high-level vision of how a post-silicon validation is obtained or is performed. You have the test inputs that go to logic, and the trace signals are transferred to a trace buffer. You see the blue rectangle as the trace buffer. It has 2 properties, the width and the depth. Width means the number of signals observed every cycle. So in this case, the width is 32. Depth is the number of cycles over which the trace signals are observed. In this case, the depth is 1024. Now, how do you select the trace signals? Trace signals is stored using signal restoration. So what does signal restoration means? It means, say, I said that you are choosing 2%, right? So imagine you have a scenario of 1,000 signals. So out of them, you are tracing 20. You will choose only those 20 signals which will restore maximum of the 980 signals that you are not tracing. So what does restoration mean? Let's take an example. So you have this 2-input AND gate. So in this example, anything with we'll take this 2-input AND gate throughout this slide. Anything with a red means we are tracing that. Anything with a black means we are not tracing that, okay? So let's take the first example, the top right, the top left-hand one. 2-input AND gate, the inputs are A, B, and the output is C. This forward restoration means we restore the output. So if you're tracing A and C state is 0, know for sure the state of C is also 0, right? The second example, you're tracing A and B, you know the states of A and B are 1, C is 1. So you're tracing to one signal and you're restoring the other. Backward means you're tracing the output and maybe one of the inputs and trying to restore the other. So in this case, for example, if you're tracing C, see the state of C is 1, you know the states of A and B are both 1. In the second example, you're tracing C, see the state of C is 0. If you trace, you don't know what the states of A and B are. But if you're tracing A also, and know the state of A is 1, you know for sure the state of B is 0. However, in the third example, if C is 0 and A is also 0, you don't know what B is. So backward restoration doesn't work in all this, okay? We'll see how signal restoration works in an actual circuit. So as you can see, this is a very simplistic diagram of a small circuit with 5 flip-flops, A, B, C, D, and E. We're tracing C every cycle. The table on the right shows how the signal states are restored or traced. So we are tracing over 4 cycles. C is traced every cycle, so the row corresponding to C is shaded in pink. So the value 0 and 1 means the state is traced or restored. X means that the state is not restored, okay? So X means that the state is it cannot be restored. So for example, when you trace C in state cycle 0, using forward restoration, you can restore states D in cycle 1. You trace C in cycle 1, and using backward restoration, you can restore A and B in cycle 0. Now, knowing the value of B in cycle 0 and C in cycle 0, you can restore the state of E in cycle 1 and so on. You see, we are tracing just 4 states and we are restoring a total of 13 states using this. So now, how can we get back to a story of malware detection? How does trace buffer help in malware detection? So trace buffers have a unique advantages of using in malware detection. Trace buffers can be easily accessed by JTAG interface. They have hardware footprints of the software being executed. So whenever you have a executed software, it will create a hardware footprint for both benign and malicious software. And then you can create a database based on the signature of the trace signals, and then you can feed a machine learning classifier to classify whether this is a benign program or a malicious program, right? So what are the advantages of repurposing a trace buffer? It has all the advantages of HPC-based malware detection. Do not incur any performance penalty. Suppose low latency malware detection. It's very important because malware detection, we want to detect it as fast as possible, right? And low false positive rate. So false positive rate should be low because otherwise what happens if there are high false positive, a lot of benign programs will get classified as a malware. That will hamper your performance, which is definitely undesirable. So this is an experimental setup. We used an Open Python, which is an Open Spark processor built by Princeton University. We ran it on a Kintex 7 FPGA system. Several IoT botnet malware from Virus Total website. We used Gasguide and Mirai malware. A total of 400 samples were downloaded. The trace signals were obtained using the 6-set tool that was developed by me during my PhD. And we used the 4 machine learning classifiers, which are k-inverse number, random forest, decision trees, and linear networks. Okay. So this is a malware detection latency, and as you can clearly see, it's very low. So if it's a processor operating at 1.6 gigahertz, this is less than a microsecond, which is way faster than any current antivirus software. Antivirus software is running in the order of seconds, when this is running in the order of microseconds. Then it has very high true positive rate and very low false positive rate. That's very important because, as is mentioned, the HPC-based systems have very high false positive rate. We reduce the family cross-validation. So basically, you trained on one family and tried to test on another. Even in that, when you train with Gasguide and detect Mirai, we get like 75 to 80% accuracy, which is quite acceptable. With the increase in trace buffer width, what happens if you're tracing in more signals? So you get a better observability of the internal signal circuit. It's like you get a better observability of the internal variables of the value of a program when you're trying to debug the program, right? So you expect the malware detection accuracy increase, and that's what we are seeing here. And the false positive also reduces, which is very good. So to summarize, debug are very efficient in malware detection, have low latency, low hardware overhead. What are the challenges? Which signals to choose for malware detection? Different set of signals can be chosen for different malware types, and how to improve the machine learning classifier latency. So we just saw that malware detection can be done in a microsecond, but that doesn't include the time taken with the machine learning classifier. So how can you make it more faster, like with less latency? That's what is important, and that's what a bottleneck we need to solve. Now we'll go on to the next, the security. So as I was mentioning before globalization, everything used to be in-house, right? Nowadays, it's distributed across the globe. So there are various challenges. The first challenge that we'll talk about is hardware trojans. Hardware trojans are malicious changes to be designed intentionally inserted by an attacker. Let me give an example. Suppose Apple, you would buy an iPhone, right? An iPhone has an Apple chip. Now, Apple doesn't fabricate their own chip. Say Apple gives it to Samsung to fabricate the chip. Now, Samsung doesn't do that, but suppose Samsung wants to do that. Samsung inserts a circuit that will just count till 1 year and will just shut down the whole iPhone chip. So you buy an iPhone today on the 7th, today's 8th, right? Sorry, the 8th of December 2021, and the iPhone stops working completely on the 8th of December 2022. You'll only blame Apple, right? Because you see that they have built the chip. But it's not Apple's fault. It's actually Samsung's fault for creating that, right? So that's a hardware trojan. It's inserted with the intention of being stealthy. Now imagine if the hardware trojan is created in an army chip, like for an Air Force chip. Somebody is fighting the war and suddenly the whole component stops working. That can be a case for national security. It has two components, trigger and payload. Trigger is used to trigger a Trojan, as the name suggests, trigger whenever Trojan gets activated. And payload is the effect of the Trojan. Okay, how does the Trojan work? The Trojan detection can be two types, functional or side channel. Functional means whether it changes the functionality, or side channel means using some power or electromagnetic signature you can detect the Trojans. We in our lab are developing EDA CAT tools for the same. The other problems are counterfeiting, as I said, imitation of critical ICs. So it can be used for commercial benefits or subverting mission critical systems. One thing that counterfeit ICs do is, like, it's not only creating fake ICs, it's recycling old ICs. So each IC has a lifetime. So what somebody can do is take the IC, clean it up a little, and sell it in the market, an old IC, right? A reverse engineering means reverse engineering your IC and selling in the market using your own. Overproduction means, suppose you have asked the foundry to create 1,000 ICs. The foundry creates 2,000 ICs, gives you back 1,000, and sells the rest 1,000 its own. So how to defend against that? So what we are creating is watermark. You know watermark, so since all of you are from India, in Indian currencies we have watermarks, right? Like, for example, in the 10 rupee note, if you take it in front of light, you will see the picture of Mahatma Gandhi as a watermark, right? So that's a watermark which is not visible to the naked eye unless you take it in front of the light, right? So we create that type of watermark in the circuits, which will not be visible to a reverse engineer. But if he or she copies that, we can actually sue that person in the court of law. So to summarize my presentation, malware are a real threat in today's world. Hardware can be used as root of trust, as we just saw. The debug hardware has several advantages, very high true positive rate and low false positive rate. A distributed manufacturing environment introduces security threats in hardware, as we saw. And that's all my presentation. I'm open to questions. Are there any questions?
Any questions from participants? Yes, Devender, you can unmute yourself and ask directly to the speaker.
I cannot hear anything.
Sir, one question is available in chat box.
Okay.
That is asked by Mr. Turja Borua. How the trace buffers are updated once the chip is manufactured with newer malware definition?
That's a very good question, Dr. Borua. So the trace buffers cannot be updated with the signals because the chip is manufactured, right? All you can do is you can change the machine learning parameters. You can update the machine learning, what you call the weights of the machine learning units, right? So that even with the same signals, you can, with the new malware, you can change the machine learning model. But however, you cannot change the trace buffer signals. That cannot be changed. I see another question by Dr. Ananta Sekhar, which says that any practical implementation lab-type examples. Yes, as I mentioned, the HPC-based malware detection is used by Intel. Intel has a very good RSA presentation, RSA 2021. I believe it's available online, so if you can search, you will find it. And that is a very good example of how we can use HPC for malware detection.
Any more questions from participants? Yeah, Devender, you may ask directly.
Yes, sir. Good morning.
Good morning. Good morning, Devender. Yes.
Yes, sir. I am very happy to hear you, and your presentation is fantastic, and I learned a lot of things from you. Sir, I just want to know, you can suggest me such type of simulators where we can type of viruses so that we can enhance our knowledge. Yes, sir.
Devendra, thanks for your kind words at the beginning. I really appreciate that. I'm very happy that you said that. However, unfortunately, I didn't understand your question properly. Can you please repeat the question? Apologies for that.
Yes, sir. Actually, I just want to know, is there any type of simulator or is there any type of platform is available where we can implement such type of small viruses, yeah, or we can implement a malicious program so that we can test ourselves and is there any possibilities are there so that so that we can enhance our knowledge.
Sure. So that's a good question. So there are a lot of virtual box kind of setups where you can run your malware. You don't want to do it on your own PC that will infect your PC. And the malware at the end of the day is a software, right? So if you do some kernel programming and develop a program to change your kernel, like for example, I can give you an example. You can create a program that will hack your ls command. You know, the ls command is used to list your files, and when you put the ls command, it will do something different. That itself is a malware. So you can pretty much do this kind of things using kernel program. Okay. So,
Okay, sir. Thank you, sir.
and thanks for the question. The answer to the Gurum's question. Why? And as far as I know, it has, because my students used it. As we speak, let me just check it once more on my website, but they had it. So yeah, there is a login options. If you log in, okay. I'm not sure how to create a login, so you have to probably mail them and create a login because my student created it. So yeah, so it is invitation only. So if you go to the about link, you will see that you have to mail to melissa97@virushcare.com. If you mail to her, she will. Okay. I hope that helps you, Dr. Guru. So Dr. Warua, to your question. Can you please speak up?
Yeah. So continuation of the previous one. Can I? Are you able to hear me?
I can hear you pretty well.
Yeah. Okay. So just the continuation of the previous question, you said can update the machine learning and algorithm or weights to it. So just what would be the process of it means to update or change the weights of the machine learning models?
Oh, okay. So the machine learning models are that's a good question actually, Dr. Borua. Machine learning models are typically stored in DRAMs, right? The weights are stored in DRAMs.
Yeah.
So you can pretty much update them over the also. It's like updating a memory.
Then also it is kind of we are going towards software related updates, right? It is moving from the hardware related. So the topic I understand it is more of like hardware oriented malware detection. Rather, when we are changing the machine learning algorithm, we are again going to the software way, right?
Not really. I wouldn't say a software. You are still in the hardware space. The signatures were created using HPCs or ETBs, which are hardware. So the basic idea was that you are creating hardware signatures and not software signatures. Does that make sense now?
Okay, can you repeat that once more? I couldn't hear in between. There was a break.
Right. So I said that the signatures that we are creating are hardware signatures and not software signatures.
Okay.
So that's why we are saying software based. After the signatures are created, what you do after the signatures are created, that's a different story altogether. Okay.
Okay. Understood.
But
yeah. Thanks, Dr. Basu. Thanks.
No, thanks for the question.
Dr. Basu, this is. Hello, Dr. Basu.
Just hold on a moment. I think we have a question in the chat window from Dr. Patel. Can we protect buffer flow attack using antivirus? Yes, of course. We can do that. We can definitely do that. You can try it yourself. Okay. Okay, Dr. Vaidyanathan, please. Sorry for stopping you because we had a question in the chat.
That's fine, Doctor. It was a wonderful session. It was a very good insight on a new way of security. Thanks a lot for that. I am into the cybersecurity domain, so I am a little curious to understand I mean, all said and done, it's going to be a hardware protection. So, how does the heuristics way of scanning or the cyber threats or the threat intelligence logic or the kind of threats which are emerging on a day-to-day basis, the ongoing one or the day-to-day one or the upcoming ones. So how far the hardware protection can give protection to such kind of threats, and going further, in case if there is any new threat or something, whatever has been embedded in the hardware, how can that be enhanced? I mean, it is a kind of an addition to the previous question. How can that be, how frequently that has to be upgraded or enhanced to take care of the ongoing threats?
That's a very good question. That's a very good question, Dr. Vaidyanathan. So the thing is that this is still in a very infant stage, right? Still researches are going on, and we don't have a product on this yet. Until we start trying to productize it, they have a separate team for this, and I hope it will be productized sometime early next year. By next year, I mean 2023, not 2022, because we are already in 2022, almost there. So that will probably take some time, and then we will have this protection. And the second question was, how can we protect against new attacks, right? So of course, as I mentioned, the new attacks can be done in two ways. If you're doing in HPCs, the advantage is you can always change the HPCs that you monitor, and then change the machine learning model, as I answered Dr. Borua's question. The other thing that you can definitely do in ETBs, the advantage is, unlike HPCs where you're monitoring only 4 to 6 signals, in ETBs you're monitoring like hundreds of thousands of signals. You have a huge budget which you can monitor, and this huge budget can help you actually get a feature selection. You can select only these type of features that you want to do for your machine learning models. In both cases, you can easily adapt yourself more tunings, and these tunings can be done on top of this. So basically, the user can have a super user permission to model that tuning. So that can be easily done. That's not a big deal. Okay.
No, let me just be more specific on this. Suppose in case if one final version of this hardware security has been released, version 1, for example, and all the corporates and individuals around, all the devices start using it, for example. Yes. So in that case, okay, in case if a hacking group, okay, wants to target this, okay, how vulnerable is this hardware? Because they pretty well know what is there inside, and the upcoming threats are not going to be handled. I'm talking about, in terms of hours or even days together. Okay, I mean, it's getting launched today, and tomorrow I plan to attack this. In case if the hackers group, because they definitely in the darknet they work in this mode only.
Right.
So in such cases, how vulnerable this hardware security, or will it sustain for a long time even after the first release? So I'm just curious to understand how is this going to be taken care of?
Good, that's a great question. So there are two aspects to it. One aspect is the hardware-based signature generation. The other aspect is the machine learning part, right? Now, if your question therefore has two parts. Let me answer the difficult part first, the machine learning part. Now that totally depends on the machine learning classifier. So every day we are getting new security attacks on machine learning systems. Any security attack on any machine learning system can be translated to this system also. So that is a different domain altogether. So that's not in our hand. That's in the hand of those guys who are developing protections for machine learning systems. Now, if you ask us about the signature, the hardware signature, the HPC or the ETB signatures, whether somebody can hack them, it's really difficult. Because if you want to hack them, you really have to go inside and modify the hardware, right? So imagine, say, you have implemented this in somewhere in a remote area. Say you guys are in Sikkim. So in some remote area in Sikkim, you have implemented that, and you are in NIT Sikkim. If somebody is trying to hack that hardware from NIT Sikkim, it's impossible, because you cannot go do a remote hacking. That's the advantage of a hardware-based system. That's the reason why people are going towards hardware-based malware detection instead of software. Because software, you can always launch a remote attack. Hardware, you cannot launch a remote attack because it's physical. You have to physically change the BOAs, right? Does that answer your question?
Yeah. So can I take that as an analogy to that? Is what I think is can we compare it to the kind of Bitcoin mining which people are trying now, which takes some of them takes years together. So is that the same probability works here?
I am unfortunately I'm really illiterate on Bitcoining, so I won't be able to answer that question.
Okay, right, doctor. Thank you so lot. Thank you so much. It was a great session, and it was a very good insight.
Thanks for the kind words, Dr. Vaidyanathan.
Thank you.
So I think we have a question from Smita Dhanokar. So Smita, will you please ask a question?
Yeah, sir. Hello, sir. Good morning. It was a wonderful session. Thank you for that. Sir, actually, I am a PhD pursuing student and I was looking something to do in threat intelligence. So, can you suggest me a few things so that I would carry my research work on that topic?
Do you mean pertaining to what I told today or in general?
In general.
In general, there are tons of materials on threat intelligence. You can just Google. I don't think I will be the best person to answer that, especially when we have Google. It's not like 1990s when there was no Google. But if you ask to pertaining, especially pertaining to what I talked about today, you can actually look at a lot of threat intelligence, especially with hardware-based malware detector. You can look at some of the papers that I have written, and then you can find some of the papers that cited us or some of the papers that I cited. You will get a more thorough picture of that.
Okay.
I hope that's your question. And thanks for the kind words and good luck with your PhD.
Yeah, thank you, sir. Good day.
Dr. Basu, just one point which I missed to update. Incidentally, I was working on hardware kind of an antivirus security almost 24 years ago.
Wow. Okay, that's great to hear.
Good to see that it's coming back, and in terms of kind of blended with machine learning, it's going to be more intelligent than it was then.
Right. Great. It's great to hear that I am a successor of you in terms of research.
No.
Really.
Yeah. I was just working. I mean, you are completely into research and you are fully knowledgeable. I am currently into the management and maintaining of all this. That's it. So I definitely learn a lot of things from you. It was just mentioned that I was working at that point of time. That's it.
Okay.
Thank you so much.
Any more questions, anyone? Dr. Ray, I don't think I can hear you. You are muted probably.
Any more questions from participants?
Oh, I think there's a question from Dr. Patel also. Sir, every company shifting towards how this hardware antivirus will be implementing on the cloud server. So, because all cloud servers still have hardware, they are built on hardware. So anything that every computing platform has a hardware. So we can easily use that on top of a cloud server, right?
Okay, it looks like all of them are satisfied now. No more queries. Dr. Basu, one request is from the participant side. So could you please share your PPT slides with us so that they can get it?
Sure, I will send it by email to you.
Okay, you send me through email. I will share with them. And okay, let's. We are at the end of this session. So thank you, Dr. Basu, for enlightening on the topics of antivirus hardware. And I hope that all the participants are really motivated here to take it further in their academic career. And thank you once again for being here in spite of your very busy schedule. And that is 2 in the midnight at USA now. I hope we will get your valuable time in future too. And we will look forward for your physical presence in near future whenever this pandemic situations will over.
Definitely, I would definitely love to.
So thank you. Accept our NIT Sikkim fraternity. We hope that we will meet you again.
Thanks. So I think there's one question remaining. Let me answer that before I leave. Dr. Patel says a project from Active Directory attack.
Okay.
Yeah, I don't think anybody has evaluated that. Maybe that's what we'll evaluate in future, or you can also do Vikas if you want to do that. But I don't think I have an answer for that. I don't think anybody has evaluated that. So, but anyway, thanks everyone for attending. I really appreciate all of you listening to my talk. It's a great privilege when somebody listens to you. So I'm really happy, and thanks a lot, Dr. Ray, for inviting me. Of course, I would be very much eager to visit you guys in NIT Sikkim and have a great time there. Okay, thank you. Thanks everyone. Have a great day, everyone. Bye.
Good night. So it's over, participants. For the first session, it's over. And as per our schedule, the second session of this day will start from 2 p.m. And that will be taken by Dr. Emmanuel S. Pili from NIT Jaipur. So in the meantime, you may leave and do join in the same link within 1:55 p.m.